If something happens, my voice gets weaker and weaker as time goes by, so hope you can hear me in the back all right. Let's see, it's Mike Sanderson here. Mike would remember back on Main Street, back then it was Ohio Technical College, and then it became OIT when we moved over here to Allen Creek Drive. And of course, they only had this part of the building, and it just seemed like, wow, because you got to realize where we came from back when we were there at Main Street and over on Sunbury Road. I remember some of you might remember when we were back in it was a converted dairy, I think at the time. But what was his name? Oppenheimer, Sam Oppenheimer, that started the school, and Bell and Howell had bought it over, and they were in a growth period. And boy, did they grow! Back then, it was terrific. And I come here now, I'm just overwhelmed by everything that's happened. So I don't want to spend a lot of time on war stories. What I want to talk about tonight, and I don't know how long we have to talk, but I mean, there's a limit. I mean, I remember when I was a grad student here at Ohio State, we had a wonderful professor from Armenia. His name was Robert Kunjan. And when we were taking the graduate courses in electromagnetics, and he taught this one on Tuesdays and Thursdays. It was an hour and a half long. It was a long time back then. And he used to laugh and say, well, the mind can't retain any more than the feet can endure. I can talk to you all night on this stuff, but you reach saturation after a while. But what I want to do is ostensibly our topic is going to be about our power systems. Right? But realize who this guy Tesla is. I hope I can impress upon you the fact that the 20th century would not have been what it was without this guy. Electrical engineering wouldn't have been what it was. He certainly was very important. The pictures that are painted of him, though, I mean, could you control that word? Because I want to walk closer over here. We get this picture of him as a crackpot or senile or something like that. And that, of course, is not at all the case. He was vice president of the IEEE for 2 terms. When the underlings were people like Steinmetz and things like that. A lot of people don't understand what his professional credentials were. So I'd like to start with his professional credentials. Let's see. The purpose of the slides for transparency is twofold, to give you an idea of what I'm talking about, but it's to keep me slowed down so that I don't go too fast. And this is what we want to talk about tonight, right? I want to talk a little bit about professional credentials, so you know who he was, and why we owe so much to this guy. He didn't just make big sparks. He maintained that sparks were a waste of energy. And of course, they didn't have National Science Foundation and places like that to go and get granting. So what you had to do is you had to get patrons. And so you had to put on a nice show for your patrons. And this was a nice way to attract funding. Right? But he was interested in doing very important things. And in fact, the North American power grid was conceived and patented by him, right, in the late 1880s. And of course, he's important because he makes AC power transmission possible. He's the guy that chose 60 for 60 hertz. Let's see. He was indeed nominated. This came to light while I was at Battelle. A lot of the history on this guy is finally leaking out. He was indeed nominated for a Nobel Prize, undivided Nobel Prize in Physics in 1937. The Nobel Committee opened up their records it must have been 1987 because it was 50 years after this, and he's the last one that they've got on the list that they had. But he was, and the guy that nominated him for the Nobel Prize, Felix Ehrenhaf, was the chairman of the physics department at Vienna. Was one of the people that nominated Einstein for the Nobel Prize in 1921 for electric spectacles. I want to talk a little bit about Tesla coils, because some of you have built one. Right? And I want you to see that they are not LC networks. They're not lumped circuit stuff like you learned about as a sophomore. They are, in fact, transmission lines, like you learned about when you took your course in microwave theory, and you plot around a Smith chart. In fact, you can take Tesla's data. We have a nice example here from, I think it's November 7th, 1899. His diary was published back about 20 years ago while he was out of Colorado Springs. And you take his very data and plot it on a Smith chart, and you can see exactly how he tuned that thing. He didn't tune it like a lumped circuit. And why is this important? Well, to undergraduates, it's important because it really underlines the distinction between lumped circuit analysis, which is important, of course, and distributed circuit analysis. And you can pass from one regime to the next as you look at Tesla's work. He's the first guy to really understand this stuff. And of course, Steinmetz comes along and works out a lot of the transmission line theory about 10 years later. So we'll look at lumped circuits, wave propagation on helices, and this forms the foundation for Keshe resonator theory and RF signal generators. I'd like to tell you a little bit about some of the work that we did before we came to Battelle, and then what we did at Battelle was some of the ball lightning work that was there. Prior to this work, people had never been able to make ball lightning in the laboratory. We found out how Tesla did it, because he described doing this, and how he shot it through windows and things like that. If we have time, at least I'll show you some of the pictures. Okay. And this work was done back about 15 years ago. Terrestrial resonances is where he was working in Colorado Springs, and he had already developed the North American power grid. Niagara Falls was already in place. That was put in place in the 1890s, and he was working on something that to him was even bigger than that, and that's kind of where he never finishes that work. Right? And he goes back to Long Island and works on it. This Long Island plant's still there today, but it's owned by a photo company. And right near Vince, when you worked there at
Brookhaven?
Brookhaven, yes, right next to Brookhaven. And it's just down the road, it's like 2 miles away from Brookhaven, where Tesla had this Long Island lab. I won't have time tonight to tell you about Tesla and the origins of radio astronomy. Fascinating history. It's on the internet. We wrote a paper on it. I have a couple of copies, but you can get them off the internet. There's a Tesla webpage. The Tesla Memorial Society of New York has a webpage, and they asked us for a paper, and we've given one in Belgrade, Yugoslavia, back about 10 years ago. So we just made it appropriate for the internet. The thing about it on the internet is that when we rebuilt Tesla's receivers that he used in Colorado Springs, you could hear this certain set of beeps, all right? And so what we give you there is the paper that really traces the origins of radio astronomy. What's the guy's name? Oliver Lodge tried to detect the sun with RF in the 1890s and failed, all right? His receivers weren't sensitive enough. Well, Tesla's at Colorado Springs, he was able to make extremely sensitive receivers. His receivers went right down to the noise floor, all right? Now, the frequencies Tesla's operating at, he was operating at frequencies around 5 to 20 kilohertz or so. What you're limited by is atmospheric noise. Now, radio astronomy today, of course, is all done 6 megahertz and above, because they think of the ionosphere as a zero band path below that. And that is not the case. In fact, if you look at the transmission factor for the ionosphere, there's a window, and the window extends from about 1 kilohertz up to about 10 or 15 kilohertz during solar minimum. Right? And it's present because of magnetoionic theory, because the Earth has a magnetic field. There's a magnetic bias on it. It makes this window open up down there when you have a period of low solar activity. We've got all this documented on that internet paper, and I'll refer you there, and you can actually click on it and hear the recorded response of one of Tesla's receivers during a Jupiter storm, because we think it was Jupiter that he heard, right? Because when we built the receivers during a period of Jupiter storm, which you normally hear up to 20 megahertz, 21 megahertz. Those of you that are hams, if you are alert to it, you can hear these storms that occur whenever Io passes through a path of Taurus around Jupiter and so forth, and emits very strong radiation towards the Earth in sort of a beamed pulse. And the EIRP is only about 10 gigawatts, right? So that by the time it gets here to the Earth, it's a substantial signal, but it's down near the noise floor. It takes a very sensitive receiver to hear it. Tesla invented a negative resistance. Today we look at it as a super regenerative receiver. He's using that in 1899, and we give the documentation. Anyway, I'm going to mention that because what was Tesla doing? He was listening to atmospheric storms when this occurred, right? Carl Jansky is doing the same thing at Bell Labs in the late 20s. He's listening to atmospheric storms. And he's got a nice Bruce array, which is a phased array of vertical elements. The dual section. You've seen the pictures of Jansky. It's the original radio telescope. They've got a model of it down at the National Radio Observatory in West Virginia. And it's a phased array. It's looking at the horizon. And what happened was, as the Milky Way passed through the beam of the antenna, background noise would come out. Jansky's famous 1932 paper shows a picture of him pointing at the Milky Way saying that's where the signals are coming from. But he was doing the same thing that Tesla was doing, that is trying to determine where the storms were coming from, atmospheric noise, and its effect on communications. All right. Anyway, that's all in this last thing. I doubt if we have time to get there. Let's see. There's another obligatory transparency. About 1984, which I guess was the 100th anniversary of the IEEE, realized that the IEEE was originally the American Institute of Electrical and Electronic Engineers, and the AIEE was formed in 1884. The Institute of Radio Engineers was actually formed in 1913 or so. By the way, Tesla's technician, the guy that was giving me the soldering iron, his name was what was his name? Fritz Lowenstein. Right. Interesting thing about Fritz Lowenstein, when they were making the original Frankenstein movie back in the 30s, you'll recall that Dr. Frankenstein is there, and this is an abomination because these things happen. They really took off on Tesla, but because they got all these Tesla coils and spark generators and things going in the back. What was the name of the guy that did all the special effects? I'll tell you in a minute. Him radio operator. But Dr. Tesla is there, in the tower, getting ready to do his big experiment. And he goes over and he listens to the earphone, and he turns and says, "There's a storm coming, Fritz." And the Fritz is Fritz Lowenstein, who was actually Tesla's assistant in Colorado Springs. And now, who was this Fritz Lowenstein? He's the guy that invented the shaped plate capacitor. On radios, the old radios used to have a linear wavelength dial. And what Fritz Lowenstein got the idea, well, if I shape the plate of the capacitor, I make so that it's linear instead of if I just have it change directly proportional to the shafting angle. Lowenstein is also the guy who first patented the Class A amplifier. Now, you guys all learn about Class B and Class C amplifiers and so forth. Class B is switching amplifiers. Somebody had to invent these things. Well, who was the guy that invented the Class A? It was Tesla's technician. His name was Fritz Lowenstein. Himself a very famous guy. He became the first vice president of the Institute of Radio Engineers. Right? So you got to realize, these are the people. Tesla was not a crackpot. He was a very precise engineer with a formal engineering background. He held 4 bachelor's degrees, mathematics, physics, mechanical engineering, electrical engineering. He got them all in 3 years, I think, from Graz Polytechnic Institute, which was, that was a pretty good school there in Austria. Then he went to graduate school at Prague, attended there, did not complete his Ph.D. at Prague. Later on, he was awarded an honorary Ph.D. from Prague University, gave him one. But instead, he needed the funds. He went to very famous thing that occurs on a frosty late February afternoon, just as the sun is setting, when Tesla gets the inspiration for the rotating magnetic field and is able to conceive of a brushless induction motor. He makes an AC motor, and that's really what makes the 20th century possible. Anyway, these are the so-called 12 apostles of electrical engineering. Right? The thing that I'm surprised by is that when you look at these guys, you just wonder, well, okay, Tesla sits in the middle of all of these, by the way. You just wonder, how did some of these guys get here? I just wonder, I suppose the Babbage is there to make the computer engineers happy that it belongs to the IEEE. But, you can think of ones that ought to be there. For example, Dr. Benjamin Franklin, really the father of electrical engineering. Right? I remember when I was interviewing for my position at then Ohio Technical College over on Sunbury Road, Jim Ayers and F. Roger Hess. I don't know if some of you remember Roger Hess before he left, and I guess went out to start a DeVry school in Kansas City, as I recall. They were sitting there. They wanted to make sure that the people they hired in could speak English and could communicate with the students. And so they asked me a question. They said, "Well, who assigns plus and minus to electrical charges?" And of course, every double A, what? Yeah, right. Everybody knows Benjamin Franklin. Franklin does some incredible work. If you've ever read the correspondence with, was it Peter Combs? The guy that really does a marvelous job explaining all this is Millikan, as in the Journal of the Franklin Institute back in about 44, 45 or so. If you ever get over to the OSU library, dig that out and read Millikan's lecture on Franklin. It's an astonishing thing. Okay, what is engineering? Most of you guys, somehow or other, are related, your chosen profession. What is it? When I first joined up here, there was an accrediting agency called the CPG, the Engineering Council for Professional Development. And it's since been changed to, I think, ABED, or I don't know, I lost track of all those guys. But they had a definition. They had a definition of what engineering was, what engineering technology was. And I forget engineering technology, what the definition was, but the definition of electrical engineering, or of engineering, always stood out in my mind. And that is that engineering is that profession which utilizes the resources of the earth for the benefit of mankind. Wow, that's almost theological in the definition, But that's what engineering is. You got to scribble it down because someday somebody's going to ask you what engineers do. And what do we do? We utilize the resources of the earth for the benefit of mankind. And now, that would have worked back in the 60s. And now, boy, it has to go even beyond the earth. By the way, the work that's currently going on Mars is really an outgrowth of Tesla's 1898 patent. He's the guy that first develops and patents remotely controlled robots. Right? He'd be delighted with what's going on today. This is, of course, Tesla in his late 70s in his office, and he was indeed every bit a mechanical and electrical engineer. He not only would work with his hands and build things and make things. We're lucky in engineering. Think of the other professions where they don't have what we've got. We can sit and think real hard, dream up something in this cognitive realm, reach over there. People that can't see or understand what we're doing at all, reach over there, get it, bring it back here after we've done the analysis, and build that thing and set it on the table and sit there and wiggle and do exactly what we dreamed it would do. Isn't it amazing? We have that creative power to be able to do that kind of stuff in electrical engineering. Who was Nikola Tesla? All right. I'm trying to tell you. If we were trying to put together his curriculum vitae, all right, and what would you put on his resume? All right. Well, here's his education. Austrian Polytechnic Institute. And by the way, it's 1856 to 1943. Right? He dies in the middle of In fact, he dies on Orthodox. His father was a Greek Orthodox priest. He dies on Orthodox Christmas Eve, or Christmas Day, in 1943, January 7th, 1943. Austrian Polytechnic Institute of Graz, separate baccalaureate degrees and so forth. Natural philosophy was called physics, or we call physics today. Back then it was natural philosophy. Because you go to England, you still take some courses in that. Honorary doctorate degrees from Paris, Columbia University, Vienna Polytechnic Institute, University on and on, Beograd, Yale, Grenoble, Sofia, Prague. I forget how many, but I think he has something like 13 honorary degrees that are conferred on him over a period of time. Professional society. He was vice president of the American Institute of Electrical Engineers from 1892 to 1894. 2 years, all right? He was a full fellow of the IEEE, the AIEE back then, right? In fact, in 1892, the AIEE elected him as its representative to go to the Electrical Congress in Frankfurt, all right? And he does other things in 1892 on his way. He stops off in England where he meets people like Dewar, you know, the guy with the Dewar, the low temperature stuff, and Lord Kelvin, who becomes a very close friend of his. And while he's in Germany, he meets Hermann von Helmholtz. Hears about him and comes to New York to meet him. Von Helmholtz, and he goes to Bonn because the work had just been done by Hertz, and he confers with Hertz, all right? I mean, so he was very active professionally, and I'll show you something that he does with Hertz's work in a few minutes. Awards. Let's see, the Fellow of the American Association for Advancement in Science. He did some work on electrotherapeutics, which is kind of peculiar, but the American Academy of Sciences, American Philosophical Society, National Electric Light Association, which was big back in those days. And let's see, the Society of French Physicists, and the British Institute of Electrical Engineers, the IEEE, which is British. And in fact, the president of the IEEE in 1943, I think, was a guy by the name of Eccles. Eccles is the guy that invents the flip-flop circuit, all right, that most of us in EEs are aware of. Eccles delivered a eulogy to Tesla in 1943 on his passing. He said he was perhaps the greatest inventor we have on our list of members. All right? So you got to realize he's not the kook that comes across when you see the news media do something about Tesla. Don't pay attention to it anyway. 250 patented inventions. What did he patent? Well, he patented the rotating magnetic field. He's really the discoverer of that. Now, that's an important concept, of course. Right? The induction motor. He makes AC motors, brushless motors, okay. The AC polyphase power distribution system, which is what, of course, is used universally today. I mean, the North American power grid was in his mind. Right? Now, what do we got today? We've got essentially the same grid with a lot more instrumentation. He's the guy that comes up with couple-tuned circuits. Now, the tuned circuit is invented by Lord Kelvin in the 1840s. But Tesla's the first one to use couple-tuned circuits, and we'll see how that plays in here in a little while. He has legal priority. The Supreme Court recognized him as having legal priority over Marconi in 1943, a very famous lawsuit that was litigated before the Supreme Court. And they recognized Tesla as the inventor of radio, right? Or wireless communications, right? He invented RF oscillators. He's the first guy to invent regenerative detectors, actually prior to Edwin Armstrong's work on regeneration and super regeneration later on. Negative resistance devices, right? Distributed resonators, voltage magnification by standing waves, helical slow wave resonators, logic gates for secure RF communications. I don't have time to stop talking about that, but he invented and patented the electrical logical AND gate. Of course, we could go back to Boole and all those guys doing logic on paper. Right? He's the first guy that actually implemented electrical circuits, switching circuits for communication purposes, and it patented, you know, in 1898. You can read the patent. High field emission, charged particle beam, switch capacitor voltage magnification. You've all learned about switch capacitor power supplies, all right? He patented the switch capacitor power supply in 1893, right? You can find it in one of the claims that he's got. You he charged up capacitors in parallel and discharged in series, and 30 years later, Cockcroft got credit for it. Okay? Charged particle beam, switch high voltage discharges, lightning protection, flightless turbines, vertical takeoff aircraft honors. The Tesla was adopted as the unit of magnetic induction, instead of Webers per square meter, in 1956. And the IEEE created the Tesla Award in the Power Society. Okay. Well, you can see what I'm trying to do here is spin that gossamer web of enchantment. If I can make you understand the stature of this man before we get into what he did, I got you in the palm of my guitar. These are certain tributes that various famous scientists. This is what people said about Tesla. This is Lord Kelvin. Now we recognize Lord Kelvin is the guy that really formulates conservation of energy. How did Kelvin formulate conservation of energy? What Kelvin did was, and every EE studies this in your sophomore circuits course. What Kelvin did was he took a Leyden jar, like everybody's been using prior to him. This is the 1840s. And he took an inductor. So he combines Benjamin Franklin and Cavendish with Faraday or with Joseph Henry. He takes the two, he charges one up, and then he brings the two together. And he gets an oscillatory discharge. And he's the first one to sit down and write that second order differential equation that we all know you can write by heart, couldn't you? The second, whatever the function is, like dt squared plus 2 alpha, the f dt plus whatever we're making up. Lord Kelvin is the first guy to do that. And he's the one that figures out that whether alpha is bigger than omega or smaller than omega, you get underdamped, overdamped, and critically damped. Okay, Kelvin does that and formulates the principle of conservation of energy. And then people try to use that to determine the age of the Earth and all kinds of things over the next few years after that. But Kelvin said, Tesla has contributed more to electrical science than any man up to this time. When did he say this? He said this, I think, in 1896. Right. And Lord Kelvin had served on that committee at Niagara Falls to decide whether they were going to, remember the Battle of the Currents, whether they were going to use DC or AC there. And that whole thing at Niagara Falls, Tesla, somewhere, I forget where it is, has an incredible discussion of why Niagara Falls. He says, when you look at it, he says, it's as though the Creator engineered this whole thing so we could make electrical power at the falls. He says, if you go way back up there in Canada, to the watershed up there, you can see how all that energy, all collected, comes down to Lake Superior. And then it passes through it's really amazing how he describes this thing, and then goes to this big holding tank that's shallow, Lake Erie, and then finally you get to this large change in potential, so that you're able to convert all this kinetic energy to potential energy to kinetic energy and generate electrical power. But the way he describes it is just the way an engineer would describe this electromechanical system. Okay, I need to get carried away here. Let's see. Bid me this course, and I will enchant thine ears. Eccles was the president, actually, in London. The greatest adventure we have had on our roll of membership. Sir James Fleming, Tesla captured the attention of the whole scientific world by his fascinating experiments. What did Nobel Prize winner say? Niels Bohr went to Belgrade in 1956 when he said this. He says, it's with deepest admiration we think of how Tesla could accomplish this great achievement. This is Niels Bohr now, okay? Ernest Rutherford, Albert Einstein. Tesla was an eminent pioneer in the realm of high-frequency currents. I congratulate him on the great successes of Röntgen. William Bragg. Bragg was one of the Nobel Prize winners. Compton, Millikan. I'm sending Tesla my gratitude, my respect, overflowing many. They weren't saying this about a crackpot or a kook. This was a very brilliant man. We only get a few people like that, every millennium. Tesla certainly qualifies as one of them. Now, presidents of the IEEE. This guy, Buck, is a very interesting character. This work of Nikola Tesla and his great conception of the rotary field seems to me to be one of the greatest feats of imagination which has ever been attained by the human mind.